evaluation question. Okay, so thanks very much for the help before the break with the module evaluation questionnaire. If you had any problems getting that to work, then you'll be able to do that later on. But please do, because it's really helpful for us in terms of making sure that we keep things going forward. Okay, so what I'm going to do is the very last lecture of new material is to look at Z transforms of multirate. DSP. And some of these can end up looking a little bit strange, and in particular the second half of this is slightly advanced material, so don't worry if it looks a bit odd to start with. So let's look at the type of system that we're building. So we're building a system x of n coming in, and we want to look at what happens to its Z transform, in this case for an interpolation or upsampling to some y of m. And we want this upsampling to be by a factor L. So if we just want to write this down as normally how we would write it, we'd say y of m. Well, let's have a look maybe at a picture for what this looks like. Here's our x of n coming in. And let's suppose that y of m, let's suppose L is equal to 3. That means we'll have those samples, but we will also have another 2 samples in between each one. So this has 3 times the number of samples in y of m. So this is just the zero stuffing part. Zero stuffing here. So we could say that if y of m is divisible by 3, then we'll get the corresponding one from x of n. So we might get here 0, 1, 2, 3. Here we get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So y of m is x of n if m is equal to Ln, and it's 0 otherwise. So this is just saying, in the terms of a formula, what this upsampling process is doing. Now, actually, we can get this in another way using a delta function. We know that if we want something that's true when m is equal to Ln, we can build a delta function using its sifting property to do that. If you remember that the sum, let's put this up here out of the way, that the sum of delta of n f of n from n equals minus infinity to infinity is equal to, what's that going to be equal to? F of 0, yeah, f of 0. So actually, if we want something that's true when m is equal to Ln, we calculate this for delta of m minus Ln, and then we sum up over all the n's. So we get the same result by saying y of m is equal to the sum over all n's from minus infinity to infinity delta of m minus Ln x of n. So you can check that this is going to give you the same answer for this whenever m is equal to ln, and that value of n, that's the value that we pull out here. This is one of the bits that makes this a little bit advanced, because you have to sort of know that this is something reasonable that you can do before you try it. Now let's see what happens if we take the Z transform of that. So we're looking to see what the Z transform of y is in terms of x. So let's try Z transform. So in general, the Z transform y of z is equal to, well, let's just write this down, y in terms of m. So what is the Z transform formula? Anyone remember this one? Yeah, so it's the sum over, in this case, m is minus infinity to infinity of y of m, z to the minus n. So that's this sum from m equals minus infinity to infinity of y of m, and y of m is itself a sum from n equals minus infinity to infinity, delta of m minus ln, x of n, z to the minus n. Now, as you're probably used to doing by now, if you can't think of anything else to do, let's swap the order of summation, because it's a linear system. So we'll put the summation over n's first, from n equals minus infinity to infinity, and then the sum over m, but actually x of n in here is not dependent on any of that, so we can just pull the x of n out here. And the next one is the sum from m equals minus infinity to infinity, delta of m minus ln, z to the minus m. Now this is a delta function, or a Kronecker delta in this case, operating with a sifting property. When's the delta going to fire, if you like? When is the delta non-zero? When m is equal to ln. Yeah, so this time, up here, it was n that we were summing over. Here now it's m we're summing after. So actually, what this pulls out is the value of z to the minus m at m equals ln, which is equal to z to the minus ln. So sure enough, this next line is the sum from n equals minus infinity to infinity x of n z to the minus ln. Which is sum from n equals minus infinity to infinity x of n z to the minus l to the power n. Now this looks sort of like it could be something familiar. Let's just take a corner out of this page here. What's the Z transform of x of z? That is the sum from n equals minus infinity to infinity x of n. Let's call this one z tilde, so we've got a different z. Z tilde to the minus n. So actually, what I've got down in here, I probably should have put plus L and minus n up here to make it easier. This is the Z transform of x, but instead of using z, we've got z to the power L. So this is actually the Z transform x of some z tilde with z tilde equals z to the L. Or in a simpler way, you could just write it as x of z to the L. So, for example, e.g. for L equals 2, y of z is equal to x of z squared. So in one sense this is sort of quite nice, but quite surprising as well a little bit, that we come out by doing this upsampling or interpolation. What we've got is the Z transform has changed the value of Z that we use. So instead of using an ordinary Z, we use Z squared. And if you think of it in terms of angles, if our Z was on the unit circle, we would go round twice as far on the unit circle, because if you square something on the unit circle, it multiplies by itself twice, so the angle doubles. The angle of rotation doubles. So this is nice. This is the easy way round. We can also look at what happens when we do downsampling. And downsampling is slightly more tricky to do, but we get a similar result. And what we'll actually find is that we can show that upsampling followed by downsampling in Z transform space will end us up at the same place after we finish. And that's going to be one of the exercises for the last bit of the tutorial sheet. But we've got this so far. This is just y of z is x of z to the power L. So it's quite a nice result. So that was upsampling. I'll keep that on there. Let's now try downsampling. So downsampling. Now we've got our x of n coming into a downsampler, downsampled by d, and out comes our y of m. And notice I'm using, again, n and m, two different values because we've got two different sampling rates, so it's easy to keep track of those. So this time, the formula for this looks a bit easier because y of m is just every dth value. If we think of, here's our x of m, here's our x of n, our y of m, our x value might have certain values like this. We only take, suppose we're downsampling by 3, we take this one, take this one, we take that one. So we only take every third sample. So y of m is x of dm. So for the 0th one we take 0, for the first one we take the 3rd, for the second one we take the 6th, and so on. Now, in order to relate these m's to each other, we want to write it as, in terms of x of m, we're going to use this sifting property again. We can write x of dm as a sifting operation from n is minus infinity to infinity, delta of n minus dm, just do the same thing, of x of n. So this is written in a similar way to the way we had it before. So if we look back at this previous example, that's what we did. Let's bring that back up here. That's what we did here, just for the downsampling, upsampling here rather. This is downsampling here. So you can see it's very similar to what we did here. So here in this case, our input n has got to be equal to dm. Here the output m was equal to ln. So it's very similar to what we've done. So now let's look at what we get from the Z transform. So y of z is, as we said before, it's the sum we're over m. So it's from m equals minus infinity to infinity y of m z to the minus m. So that's the sum from m equals minus infinity to infinity, and y of m we've got this expression for instead, so that's the sum from n equals minus infinity to infinity delta of n minus dm x of n multiplied by z to the minus m. And as before, we change the order of our summation. So this is now we're summing over n is minus infinity to infinity, and x of n comes out from there because it's not dependent on the m that we're summing over next. Next is sum of m from minus infinity to infinity delta of n minus dm z to the minus m. So this one, this sifting property here, this pulls out z to the minus m when n is equal to dm. In other words, when m is equal to n over d. So that's equal to z to the minus n over d. So that gives us our sum from n equals minus infinity to infinity x of n z to the minus n over d, but actually it hasn't got rid of all of the total samples in here because we've got too many m's to go over in this point. So we have to, for now, we have to keep this sum. So what we've been able to do here is to convert the z to the minus m to the z to the minus n over d, but we've still got this to work out what happens to that. So over here, this, if we end up with this, this point here, this gives us 1 if n mod d is equal to 0. So if n is exactly divisible by d, then these will cancel, or give us a 1. It'll give us 0 otherwise. And so let's see how this comes from. So we could write this, if we wanted to, as a delta function but a periodic delta function here. Delta function of n mod d. So delta of n mod d, if we want to write this down. So this bit is actually quite tricky. But let's have a look at how we could do this using a Fourier transform. So, discrete Fourier transforms we can take of these delta functions. But let's just go back to a bit of first principles of this. So we want to get this discrete Fourier transform. Let's just recall our discrete Fourier transform to see where this is coming from. DFT, just write G of K from some function G of N is the sum from little n equals 0 to n minus 1, G of N, Wn to the nk, where our Wn is e to the minus j 2 pi over n. So this is our twiddle factor. We did this back in when we were doing the discrete Fourier transform and the fast Fourier transform. We've got an inverse, the IDFT. G of n is 1 over n. The sum from k equals 0 to big N minus 1, big G of k, Wn to the minus n k. That's our inverse discrete Fourier transform. And these work for periodic G of n and big G of k of period big N. So now let's see what we get if we use big N equals D, our decimation factor, and G of N will substitute for this delta of N mod D. N D. Now we know that this is periodic, delta of N mod D. It's got period D because every time n is 0 or d or 2d or 3d, this will be an extra delta function at that point. So let's try calculating the DFT of that. So our G of k, if we're using this substitution, is the sum from n equals 0 to n minus 1. This is just the definition of the discrete Fourier transform. Delta of n mod d, Wd to the nk. Now let's look at this delta n mod d, because this is equal to 1 when n is equal to 0 mod d. So that means that if we sum up all the values of here, all of them are 0 except for the one where n is equal to 0. So it's actually Wd to to the nk at n is equal to 0, which is the twiddle factor to the 0, which is 1. So that means its discrete Fourier transform is equal to 1. This is what we would normally expect for a delta function. If you have a delta function at 0, its Fourier transform is 1. It sort of has a white spectrum, if you like. So the IDFT, let's look at this from the other side. This is our G of n. So something that's got a Fourier transform of 1, the IDFT, which we had as our delta of n mod d. Let's just write out this IDFT formula. It's 1 over n, the sum from k equals 0 to n minus 1, g of k, wd to the minus nk. Now on this line, we found that g of k is equal to 1. So that's equal to 1. So this result is 1 over n times the sum from k equals 0 to n minus 1 of w d to the minus nk. So now we've got this result that somehow this slightly weird looking result here, a delta of n mod d is equal to this strange looking sum. Oh, sorry, yes. So the delta of n mod d is equal to this strange looking sum. So if we now substitute that into our y of z that we had over here, now our y of z is sum from n equals minus infinity to infinity x of z, x of n, z to minus n over d times these n's should, because we used n over d, n is equal to d here, we should have used d really for those instead of n. Would have been better to use d. So this is 1 over d, the sum from k equals 0 to d minus 1, w d to the minus nk. So we can sort of pull that back in together if we want to, but that gives us 1 over d. We can put the sum over k to start with. K equals 0 to d minus 1. Sum from n equals minus infinity to infinity x of n. The z to the minus 1 over d we've got here. W d to the k we've got here. So those things are all to the power n. So w d to the k, z to the minus, z to the 1 over d to the minus n. It's not very nice. This is why the downsampling Z transform is much more complex than the regular upsampling version. But if we think that if we want to compare this to a normal Z transform, x of z is equal to the sum from n equals minus infinity to infinity x of n. Let's call this one z tilde. Z tilde to the minus n. So you can see there's a sort of similarity coming up here, but instead of just an ordinary z, we've got some other mixture coming up in here instead. So actually what happens when we substitute the whole lot in together is that we get y of z is equal to 1 over d, the sum from k equals 0 to d minus 1, big X of, instead of z, wd to the k, z to the 1 over d. So if we compare this back to what we had, which was a much simpler version earlier for the Z transform of upsampling, we simply found that y of z is equal to x of z where we raise it to our sampling power. Here it's not quite as simple. There's a 1 over d in here, there's a wd to the k, a z to the 1 over d. There's a sort of 1 over in here, but it's a bit hidden. In fact, for a simple version, let's try what happens with z equals 2.
Maybe you can leave at 9 o'clock.
So let's keep that version and do an example of d equals 2.
Yeah, but tomorrow morning also you.
For that, y of z is 1 over d, which is a half. We've got a sum from k equals 0 to 1 of this, so we'll do the one with k equals 0 to start with. W to 0.
Final day for this
Z to the 1 over d
for this semester.
plus x of
So we should focus on
1.
finish it. So we can. Okay, let's speak. Oh,
But
did you
if
know
we
what
think
is analyzing?
what our twiddle factors are like,
What is this? Analyze.
w2 to the 0 is equal to 1, and
is
w2 to the 1 is equal to
what is
minus
this?
1.
Has to do with.
So actually this is a half
signal
of
mirroring goes to
x
do
of
a knife
z to the
limit.
half, because
Yeah.
1 over d
Frequency
is
is
a
twice
half there,
the normal.
plus x of
I don't
minus
know.
I'll
z
check
to the half.
Okay.
because I'm sure it's coming in somewhere.
So it does simplify slightly in the case of d equals 2. But this is actually quite advanced, and you'd be unlikely to come across this bit in the way that I'm now doing the module. But it is really to show that you can actually just do Z transforms of, well, upsampling is straightforward, downsampling is more difficult. Once you've got these, you can show that upsampling followed by
Yeah, it's to do with
downsampling
frequency. So it's to do with
is a sort of do nothing operation, and so that's something that you'll be able to have a go with in the tutorial. So this is quite tricky material to work through, but I thought it would be useful for you to see that you can do something with the Z transforms for these, but they're really not something that you'd want to try and do without actually having a map to know where you're going. Okay, so that's really the end of the new material for this module. I've got 5 minutes at the end to pick up any questions from anybody if you would like to stay around and ask anything. So otherwise, from there, next week we will be going into revision material. There's a tutorial still next week on the Monday morning, covering the last 3 questions of the Multirate tutorial sheet 9. And then in the afternoon, I'll have 2 hours of lectures to go through the revision material that I mentioned at the beginning. And so that's the revision plan that's uploaded onto Surrey Learn. So you can find all the questions from there, and then we'll go through those examples. So I'll talk through those questions as I go through, and I can pick up any tricky bits from there. So what I'd suggest is that have a go through those questions before looking at the solutions. Pick out things that you want to ask questions about, and then I can go through those in the revision sessions afterwards. And I'll talk a little bit about possible techniques for going through things, but you'll have done exams before, so you won't necessarily need all of those. But some things just...
Did you know how to...
This guy.
Okay, thank you very much,
Yeah.
and
Do you
I
know
will
how to
see
write
you
it
in the
in
lab
pretend
tomorrow. Bye for now.
Ah, that's the one. That's the one. I need to remember this one. 8-point FFT is different. Snap. Yeah, what's the question?
It's okay.
What the hell? I need to know this one. 8-point FFT. Impossible. There we go. That's the one I couldn't do. Nice. I hope he doesn't ask this one. Sometimes. You go. Oh, whatever, actually.
Sorry.
I was going to ask, are you going through the lecture?
Sorry?
Are you going through Prenuptial?
You go...
Are you going through Prenuptial as in the lecture? Are you going through the lecture? I mean, the Prenuptial.
Yeah.
Okay.
I still hearing about it. Use it to reversion something and do the tutorials as well. I do these 2 things.